Hello everyone, I am a mechanical design engineer employed by Hy-Tek Manufacturing in Sugar Grove, Illinois. Through the Department of Defense SBIR program, the Navy solicited interested small businesses to develop a replacement aircraft line clamp for the F-18 Hornet. The objective of this development program was to design a line clamp cushion using innovative materials that exhibit excellent resistance to prolonged UV and ozone exposure. The Navy's expected outcome is the delivery of a line clamp with greater longevity, performance, and reliability than those currently deployed on the F-18 and other Navy aircraft. To satisfy these requirements, Hy-Tek invented the Enhanced Clamp Cushion, or ECC, using unique clamp core and cushion geometry with custom-formulated cushion elastomer. When combined into a fully assembled ECC clamp, the engineered clamp geometry reduces cushion damage caused by mechanical strain, while the novel elastomer material facilitates unmatched resistance to UV and ozone degradation. During Phase 2 testing and evaluation, ECC prototypes exhibited improved aircraft line stabilization performance, enhanced reliability, and extended in-service longevity. When adopted for use on the F-18 and other Navy aircraft, ECC technology will significantly extend the mean time before line clamp failure and therein reduce line clamp maintenance burden and replacement costs. Hy-Tek Manufacturing was founded in 1984 and has been a participant in the SBIR program since 2003. With core competency and experience in mechanical, chemical, electrical, and manufacturing engineering, HMC has been awarded 18 Phase 1 and 11 Phase 2 DoD SBIR awards. 2 of HMC's Phase 2 awards have been extended to subsequent Phase 2 awards, while 2 products developed by HMC during Phase 2 SBIR work have been transitioned to Phase 3 commercialization, mass production, and government sales. HMC facilities consist of an engineering research workspace of approximately 15,000 square feet and 43,000 square feet of manufacturing workspace. In addition to its engineering staff, HMC also employs 45 highly skilled manufacturing professionals who perform in-house mass production of custom engineered products for the agriculture, mining, construction, and defense industries. An example of HMC's SBIR Phase 3 success is the high-load roller bearing, or HLRB, that is currently manufactured in-house by HMC and installed on the helicopter hangar bay doors of Navy's Arleigh Burke-class DDG-51 destroyer. The Navy's objective under this Phase 1 and 2 SBIR funding was to replace currently deployed nitrile cushion F-18 line clamps with an engineered clamp core and cushion capable of withstanding prolonged exposure to UV radiation and atmospheric ozone, while facilitating improved line clamp performance, reliability, and longevity. The Navy's investment in this development project stemmed from the rapid degradation and failure of existing nitrile clamps when exposed to ultraviolet light and atmospheric ozone. Rapid environmental degradation of nitrile cushion material is exacerbated by cushion shear and abrasion damage caused by the sharp edges of the existing metal clamp core. The eccentric geometry of the existing cushion and core also causes considerable shear and abrasion damage to the nitrile cushion when fitted to cylindrical aircraft lines. When compounded, these design and material deficiencies result in rapid nitrile cushion failure that can lead to detrimental contact between the metal clamp core and the aircraft line to which it is fitted. Rapid nitrile clamp cushion degradation and failure is therefore not just a costly logistics burden to the Navy, but also a significant hazard to proper aircraft operation, flight crew safety, and overall fleet readiness. During Phase 2 testing and evaluation, the ECC satisfied or exceeded all performance and material requirements specified in the 85052B and 85052/1C clamp specifications. The M85052/1 nitrile aircraft line clamp currently deployed by the U.S. Navy has been in use since 1984. Although nitrile is commonly used in applications that require chemical and fuel resistance, it is vulnerable to rapid UV and ozone degradation. UV and ozone degradation of a nitrile clamp cushion is illustrated in the image at the top right of this slide. As the nitrile cushion material becomes increasingly damaged by exposure to UV light and ozone, sharp edges of the clamp core shear through the brittle and weakened nitrile cushion and expose the cylindrical aircraft line to detrimental metal-to-metal contact. The top and bottom images at the right of this slide also illustrate the eccentric geometry of the Navy's existing M85052/1 line clamp that contributes to rapid shear and abrasion damage of the nitrile cushion soon after installation. Rapid failure of these legacy nitrile cushion line clamps is a persistent problem that requires frequent, costly, and logistically burdensome replacement. The engineered mechanical design of the ECC core and cushion, along with the use of state-of-the-art environmentally resistant elastomer cushion material, eliminates these capability gaps. Unlike the existing M85052/1 clamp used by the Navy, the ECC core and cushion are designed and fabricated to maintain a cylindrical shape that matches that of the aircraft line to which they are installed. A matching support structure integrated into the ECC metal core and cushion, coined the Mohawk, ensures that the elastomer cushion and metal core will not separately slide or shift during aircraft operation. This vital design feature virtually eliminates shear-related cushion damage. Comprehensive testing and analysis of HMC's current ECC prototype has validated that it provides significant improvement in line stabilization performance, UV ozone resistance, and operational longevity in harsh operating environments. The photograph at the top right of the current slide shows a fully fabricated and assembled ECC clamp. As illustrated in this photograph, elastomer cushion studs extend through penetrations machined into the metal core of the clamp to form the integrated Mohawk structure. This Mohawk interlocks the cushion to the rigid metal core and eliminates cushion sliding, shifting, or misalignment under high vibration conditions. This photo also shows the improved cylindrical geometry of the inside diameter of the cushion that promotes an improved fit to aircraft lines. The photograph on the bottom right of this slide illustrates the excellent concentric fit between the ECC and a cylindrical mandrel. ECC engineered geometry, combined with the enhanced chemical, UV, and ozone-resistant elastomer cushion, results in an aircraft line clamp that delivers much better line stabilization performance, operational reliability, and in-service longevity than that of the Navy's currently deployed line clamp. During HMC's Phase 2 ECC testing regime, the ECC passed UV ozone exposure testing at 10 times the specified duration with no signs of damage. It has passed operational temperature requirements over the range of -65 Fahrenheit to +275 Fahrenheit. It has passed fuel and oil immersion testing with a maximum 1.5% volume increase after 1 week of immersion. It passed compression set testing with only 5.17% compression set after 24 hours at 180 degrees Fahrenheit. Since publishing these results, testing has shown greater performance improvement. And the ECC passed vibration testing at an extended range of up to 1000 Hz with no damage or loss of clamping strength. The ECC exceeded all required physical assembly testing metrics delineated in the 85052B clamp specification. HMC's Phase 1 and Phase 2 ECC development was conducted using a well-organized engineering design, testing, and optimization plan that included critical development milestones. HMC engineers performed this plan in a chronological fashion that enabled follow-on ECC design optimization only after each previous milestone had been achieved. HMC first studied and analyzed the current 85052B general specification and the 85052/1C clamp specification to understand the U.S. Navy's aircraft line clamp material and performance requirements. HMC also studied and evaluated the conditions under which these clamps operate in order to identify root causes of rapid deterioration and delineate exact failure modes. Based on these results, HMC produced several promising ECC core and cushion design concepts to alleviate mechanical stress related to cushion damage, while concurrently researching and identifying promising elastomers for ECC cushion prototype production and testing. Initial ECC design variant prototypes were fabricated using in-house 3D printers for the purpose of conducting extensive testing, results evaluation, and incremental optimization. Simultaneously, candidate ECC cushion materials were evaluated according to the 85052B specification, with the most promising elastomer candidates selected for follow-on testing, evaluation, and down selection. During the Phase 1 option period, the most promising ECC cushion material candidates and best performing core and cushion geometry were subjected to follow-on prototype testing, evaluation, and incremental optimization. This work included extensive physical and chemical testing of candidate elastomer materials and the ECC metal core under simulated exposure conditions. By the end of the Phase 1 option period, HMC had down-selected 2 candidate ECC cushion elastomers for follow-on evaluation during Phase 2 work. As Slide 7 illustrates, during Phase 2 ECC development, HMC again utilized a well-organized and chronological work plan and milestone roadmap. This plan included more extensive laboratory testing of candidate ECC cushion materials against Navy-delineated specifications. This testing regime included required flame resistance, chemical resistance, and physical strength evaluations necessary to enable HMC to down-select the best-performing ECC cushion material. HMC consulted elastomer fabricators to fabricate physical prototypes of the Mohawk cushion for comprehensive physical testing. Mechanical stress and exposure testing of optimized ECC core prototypes was conducted both in-house and by certified third-party labs. Finally, using third-party laboratories, fully assembled ECC prototypes were fabricated and tested under enhanced and protracted UV, ozone, and vibration exposure conditions. Those ECC prototypes passed all testing conditions to which they were exposed. Development of the ECC focused on optimizing both the cushion and core to improve the function of the line clamp. The shape of the metal clamp core and elastomer Mohawk cushion material were both chosen and tested for this purpose. The ECC design presented herein is based on the existing M85052/1 clamp in order to ensure that it will easily integrate into the same Navy aircraft line stabilization applications. Comparing the two clamp designs, the ECC has several benefits over the current M85052/1 line clamp. The concentric shape, smoothed edges, and mohawk structure mitigates the shear stress on the cushion and stabilizes the cushion in the clamp core, reducing the mechanical damage on the cushion and increasing the service life of the clamp. The ECC cushion represents a significant modernization in elastomer materials, having much improved resistance to chemical immersion, UV radiation, and atmospheric ozone exposure. Testing has shown the ECC capable of withstanding at least 10 times greater ultraviolet light, heat, and ozone exposure duration than the M85052/1 nitrile cushion, with no signs of significant degradation. The current slide shows the path for ECC transition delineated into chronological steps. The first step is completion of incremental Phase 2 ECC design optimization and thorough material and performance testing performed by HMC and a certified third-party lab. This step will include ECC cushion material resistance testing and overall ECC performance validation for those clamp sizes most used by the U.S. Navy. HMC has already completed material testing and performance validation for 5 of those most utilized clamp sizes. The second and third steps in this process will include the U.S. Navy performing enhanced ECC testing in a laboratory environment, followed by certification of ECC for testing on U.S. Navy F-18 aircraft. Once ECC testing and performance validation has been successfully completed in these environments, HMC will of course begin mold production, prototype fabrication, and testing of each of the additional 14 clamp sizes used by the U.S. Navy. HMC is currently on schedule to complete these TRL-7 transition tasks on or before the end of Phase 2. Refinement and optimization of ECC mass fabrication processes and costs will be completed in accordance with HMC's well-organized ECC commercialization plan. As shown in Slide 10, HMC has completed a thorough study of the military and commercial markets for the ECC. The most obvious and immediate market for ECC is, of course, all military aircraft currently fitted with existing M85052/1 line clamps. HMC expects that its collaboration with the U.S. Navy during ECC development will promote rapid outreach to all other military branches also using legacy nitrile cushioned aircraft line clamps. Follow-on ECC commercialization and marketing efforts will focus on military aircraft OEMs that include Boeing, Lockheed Martin, General Dynamics, and others. These corporations often have their own material and parts qualification requirements that may be more complex and require protracted procedures to satisfy. HMC expects, however, that sharing Phase 2 ECC technical data and testing results between HMC, U.S. Navy, and those private sector firms will accelerate OEM adoption and deployment of ECC. HMC believes that the largest potential market for ECC lies in general aviation. This market includes all of the approximate 440,000 commercial and private aircraft that are currently in use worldwide and manufactured by Boeing, General Dynamics, and Airbus, among others. HMC's commercialization plan addressed the outreach and marketing necessary for success in that sector, as well as non-aviation applications for ECC in the marine vehicle, land vehicle, and agricultural equipment sectors. HMC's approach to successful ECC marketing and sales includes 1. Identifying the performance, capability, and longevity gaps between existing line clamps and that of the ECC. 2. Highlighting superior ECC performance, capability, and longevity versus that of the existing line clamps. 3. Tying those performance and longevity metrics to reduced clamp acquisition and replacement costs. And 4. Leverage improved ECC performance, longevity, and low cost of ownership to sell ECC based on exceptional return on investment. As illustrated in Slide 11, the most critical ECC stakeholders are those that will immediately benefit from HMC's successful ECC Phase 2 development efforts. These ECC transition stakeholders are separated into 2 categories. 1. Those involved in the purchase, use, and manufacture of a military aircraft, including all military branches and all military aircraft OEMs. And 2. Those involved in the purchase, use, and manufacture of commercial aircraft, including all commercial airlines, private aircraft owners, and commercial aircraft OEMs. HMC understands that the foundation for commercialization of ECC to the private sector will be successful completion of its SBIR-funded Phase 2 ECC development work. A particular benefit to HMC's ECC commercialization and marketing efforts is the fact that the legacy line clamp currently dominates both the military and commercial aircraft line clamp markets. Those wishing to learn more about ECC design features, performance, and cost benefits can contact either Mr. John Jude or Mr. John Bastin of Hy-Tek Manufacturing. Also, please feel free to visit HMC's corporate website. Thank you.